Why do we even consider quantum machine learning? When you think about the kind of technologies that go into what you use today, until 10 years ago, you were mainly using CPUs and running serial or barely parallel algorithms to learn something from data. And then, then came this explosion of computational power with GPUs becoming useful for linear algebra. And as you all know, that enabled deep learning. But then you started to run into problems with power use. And so that's why people moved these deep neural learning networks towards FPGAs and then ASICs like neuromorphic chips. Some of these ASICs are already in your phone doing the face recognition. So you already have this mix of different hardware when you talk about contemporary machine learning. And when you think about what are the things that are easy to do with deep learning, you're mainly looking at supervised problems, things that are discriminative, things that are easy to parallelize, and you typically work with deterministic algorithms. I'm not saying that this is true for every single deep learning algorithm out there, because there are other approaches, but these are the easy things to do with these resources, or the easiest things to do. So when it comes to quantum devices, I think it's worth focusing on the problems which are hard to do with deep learning or hard to do with classical computers in general. So things like unsupervised learning, generative models, probabilistic models, and things that are just not easy to parallelize. So my research really focuses on what are the kind of things in these hard domains that you can do with quantum devices. And let's take a very quick look at the scale of the quantum devices that we have today. So today we have a handful of qubits, and we can apply a bunch of operations on them, which are called gates. So this looks like the 1940s in digital computing, where you had to think in assembly, and you had to think in terms of logical operations. That's pretty much the state where it comes to writing quantum algorithms, and we can't do very big calculations, okay? A handful of qubits and a handful of gates. Then this is where we are going to be in 3 to 5 years, okay? So this is where we are today, and then we will have about 100 qubits and maybe 100 gates of depth.
What do lines and boxes represent in this?
I'm going to return to this, but the lines represent individual qubits, registers, and then the gates are operations that you execute on qubits. And so these circuits will enable you to do really exciting stuff. But the problem is that the popular media hammers this message into your head that when it comes to quantum computers, you must get some exponential advantage. And to give you an idea just how far we are from this is what we need for an exponential advantage. So a dense, very deep circuit, and this 1 pixel green is where we are today, and this larger box is where we are going to be in 3 to 5 years, and that's what you need to get that exponential advantage. We are incredibly far from that. That's the whole message of this. But even if you can build this, that is going to give you some fun advantage in a bunch of problems that I'm going to go through in more detail. And that's the reason why there is a lot of commercial interest in building these quantum computers. So let's look at the worldwide landscape of who is building actual quantum computers in a commercial setting. I'm not talking about academic labs. It's very heavily biased towards companies based in North America. Like HP and Intel are not having their quantum computers here, but they are still North American companies. And China recently joined this quantum race. And to give you an idea of how much investment is going into this, so the oldest player in this game is D-Wave. They've been around for 19 years. And over these 19 years, they raised $204 million to build their quantum computer. And in comparison, Alibaba last year announced to invest $15 billion into building a quantum computer. So I don't know if you can even see it, but there's a bar here to represent how much $204 million are compared to the $15 billion. And so there's a lot of money poured into this. and it really is an arms race now. So there are all these companies trying to build these intermediate scale quantum devices. But what is quantum computing about? Like, what's the buzz about? When you think about digital computers, what digital computers do is they transform bit strings into bit strings, right? So you have some sequence of zeros and ones, and then you apply logical operations, and you get another sequence of zeros and ones. And this enables you to do arithmetic operations, additions, multiplications, and so on, which will eventually add up to word processors and deep learning networks. And if you start to generalize this, you can end up with stochastic calculations, where instead of bit strings, you operate over probability distributions over these bit strings. There isn't really hardware for this. So if you want to do something like this, then you would have to simulate it with some Monte Carlo sampling on a classical computer. And quantum computers are like a step beyond that. A quantum state is nothing but a special probability distribution. So what a quantum computer does, it has this quantum probability distribution over bit strings, and the quantum calculation is basically a transformation of this probability distribution. So in other words, a quantum computer is nothing but something that transforms probability distributions in a specific way. And since it's not a classical probability distribution, you use these well-known quantum effects of interference and entanglement to perform your calculations. And this is what gives you this power. This is what gives you this advantage. So, but then, so we have these probability distributions over the qubits as opposed to just having single bit strings. But then why do you need so many qubits, right? We want thousands of them, whereas your CPU or the processor in your phone has 64 bits and you're perfectly happy with it. So why is it that we need thousands of them? So the difference is that in a classical hardware, you chunk up your calculations into a sequence of calculations or maybe parallel sequences of calculations. But in a quantum computer, every calculation is global. So basically, you have to embed the entire problem that you have into the quantum hardware to have this probability distribution over all possibilities. And that's where you start to use entanglement. So for instance, if you chunked up your calculations into different bits, into different chunks, and run it on a quantum computer, then these different chunks could not make use of quantum effects between them. So it's very important to realize that quantum computers do these global calculations, and that's why we need so many qubits.
So instead of thinking about it as the bit width in the ALU, should I think about it as the memory size?
It's not really memory because this is what you do an operation on. You're doing operations on the entire distribution.
Okay.
So it's more like the neuromorphic chips where the memory is exactly where you perform your calculation. It's a little bit closer to that. More questions? Okay. Then, so quantum computers, irrespective of the type of quantum computers, transform probability distributions, and they do these global calculations. But there are two major paradigms, and this is where it gets a little bit confusing, so I just want to dispel confusion. So one model of calculation is what we call universal quantum computation or gate model quantum computing. So this is the case where you have a qubit here, and then you operate with gates over these qubits. A qubit is a distribution between 0 and 1, a quantum distribution between 0 and 1. So what these gates do is they operate over these probability distributions to transform them in a particular way. And the second paradigm is called quantum annealing, which is a little bit different. It's a more physical way of thinking about calculations. I'm going to explain in a moment what this is about. But basically, instead of a circuit, what you're expressing is a type of optimization problem. And then what you're getting out of the calculation is the global optimum, or a very good local optimum of this optimization problem. And it could be made universal, but the way it is implemented is actually not universal. And so in this paradigm, we are up to maybe 70 qubits at the moment, if you look at, for instance, the chip by Google. And with this paradigm, we are up to 2,000 qubits by D-Wave System, who are based in British Columbia. So the annealing paradigm, although it's not universal, and it's very specific, it's a lot more scalable. So those are, yep.
So can you always formulate an optimization problem, a binary optimization problem to one of these quantum annealing?
Yes and no. So the tricky part is that, fine, you have 2,000 qubits, but you implement them with superconducting architectures. So in a superconducting architecture, you use the same fabrication as you would use in your CPUs and GPUs and whatnot, so it's silicon-based. And since it's just a layer of silicon, or a few layers of silicon, that means that your topology is mainly two-dimensional, which means that you cannot connect all of the qubits. So in the D-Wave architecture, you have 2048 qubits, but only 6 qubits are connected. Okay, so one qubit is only connected to 6 others because the wires cannot cross. So there is this fundamental limitation in everything superconducting that you cannot have a fully connected graph. So if you have a binary optimization problem, which has some connectivity structure, then your duty first is to map it to the hardware, and then you can solve it. So to give you an idea, that if you want to embed a fully connected graph on D-Wave, for instance, then although you have 2048 qubits, you are limited to about 40 binary variables because you have to use several physical qubits to represent one logical qubit. So, yeah?
So the gate model, can that be viewed as a multiplier and the sum operators? Or
so
in the gate model in the previous slide,
yeah.
You have these little dot and the plus.
Oh, that's something called the CNOT gate. So this is called the Hadamard Gate. The Hadamard Gate ensures that when you start from 0 qubit, after you send it through this gate, it will be an equal superposition of 0 and 1, which means that if you look at it, if you measure it, then with probability 1/2 you get 0 out, and with probability 1/2 you get out 1. And what this gate does is it's a controlled NOT. So every time when this qubit is 0, it's not doing anything here. And every time when this qubit is 1, it's going to flip the value of this qubit. But now you have a superposition of 0 and 1, which means that this control is both 0 and 1, so it will execute both, so you will always have something interesting happening here. So apart from the two paradigms, in digital computing, you are used to having just the same substrate everywhere. So whether it's an ASIC, whether it's a GPU, whether it's a CPU, it's always the same silicon wafer. In quantum computing, this consensus have not been achieved yet. So as I mentioned, we have these superconducting architectures which use silicons, except that you cool them down to 4 millikelvin. Cooling them down is a bit expensive because the fridge that you need for this costs $500,000, and there are a bunch of engineering problems, and you're always restricted by this 2D topology that I just explained. Then you have photonic implementations, which use lasers. And the massive advantage of this is that you don't have to cool the system down. So these operate at room temperature, but they have other control problems. Same thing with trapped ions. In trapped ions, what you do is you trap individual atoms in between laser beams, and then the interaction between these atoms is what does the calculation. But again, so this works at room temperature, so that's fantastic. But then the problem is that I think control is relatively slow in these models. So it's unclear which of these paradigms is going to get us thousands of qubits and very deep circuits. That's why there are several companies trying all of these architectures. But most companies out there are focusing on the superconducting stuff because that's good for PR, because it's relatively simple to scale up the number of qubits, and then you can make press releases. So, do you guys have any questions about the quantum computing paradigms and the substrates? Or can we move on?
What were the problems with photonic?
a good question. I don't know so much about photonic architectures, but I think it's largely about how you create these integrated circuits. So there is integrated photonic circuits, and a major operation that you have to do in these photonic systems is something called squeezing. And you want it to be like infinitely good, but there is a big limitation, big engineering limitation of how you can do this in actual circuits. And like the first company who can get this right is going to go big, because then you can do very meaningful calculations with these photonic systems. So if there are no more questions, then I'm going to explain like what is this main limitation? Why are we limited to short circuits and short calculations? So ideally, we have this quantum processor, which is 1,000 qubits, and we just give it like 1,000,000 instructions and tell it, hey, execute all of this. But that's not how it works, because this quantum processor is embedded in an environment, and it interacts with the environment in a largely uncontrolled way. So this environment encompasses everything that we consider noise. So think about the following, for instance. Think about the system being cooled down to 4 millikelvin. So you have the quantum chip at the bottom, and then classical control goes into it, classical electronic control. So the entire thing is in this big black or white box, which is essentially a Faraday cage to shield the quantum computer from electromagnetic radiation. And fine, so you are shielded from external electromagnetic radiation, but the classical control that goes into the chip, that itself creates its own electromagnetic radiation, and that interferes with your quantum calculation. So that's part of this environment. And then you cool it down to 4 millikelvin, but that's still not the lowest temperature that you can get. So this is another engineering constraint. And then this finite temperature starts to mess up with your calculations. So any kind of noise, and whether it's superconducting or photonic architecture, you model by some environment and with some interaction with this environment. And so in a superconducting architecture, the main constraint is time. So after just a very, very, very short time, your qubits interact with the environment, and they're no longer in the state that you want them to be. That's why you have to keep your circuits short, because every gate that you put on a qubit takes some time to execute. So the more gates you have, the longer your execution time, and the higher the probability that your quantum state is no longer what you think it is, because it interacts with the environment. So the model that we have today is this hybrid classical quantum algorithm, where you do a very short calculation on the quantum chip, and then you measure things out. So you extract classical information, you post-process it with a classical processor, and then you tune some parameters, and then you go back to the quantum processor, and then you keep going back and forth. So this hybrid paradigm is what's going to exist for the next 3, 5, 10, maybe even 20 years. Keep just a short calculation on the quantum computer and do a lot of post-processing. So what are the kind of things that we can do with a quantum computer that's relevant for machine learning? I'm going to go through 4 major application areas, and the first one is optimization. But first, I want to explain to you like how exactly quantum annealing works, because that's going to make a lot of things clear later on. So imagine that you have 2 magnets. Magnets naturally like to anti-align. So if they are fixed on the same axis, then they will eventually flip. So one will be upside down. So imagine now that we associate values +1 and -1 with the configuration of the magnet. And then if you write it down, then you can say that magnet 1 is some sigma 1 variable, and magnet 2 is sigma 2. And in the optimal configuration, the product is always going to be -1. Right? Because either this one is +1 and that one is -1, or the other way around. And if you multiply them, their product is always going to be -1. So add the third magnet, and now you end up with this sum. So in the optimal configuration, the value of this energy essentially is -2. Now, make it a bit more complicated. So imagine that you can add a wall, and you can control the thickness of this wall, or how deep it goes between the magnets. So you can control how much each magnet interacts with its nearest neighbor. So this adds this coupling term between the magnets. Okay? And now you can add very large magnets outside, which create an external field. So if this external field is strong enough, then it can flip this magnet upside down. So there will be some frustration between these two, because these two will not be anti-aligned, but because this magnet is so strong, this will win out. So with this, you are adding this additional term, which measures the interaction between the magnets and the external field. And what nature tries to achieve is an energy minimum. So you try to minimize the energy of your overall configuration. And it turns out that this can be difficult to do in some settings. For instance, if all of your external fields and these couplings are roughly on the same scale, then it's difficult to determine which is the optimal configuration of all of your magnets in a system. And it can happen that nature itself gets stuck in a local optimum. So it's possible that it achieves some low energy solution to this problem. It naturally equilibrates to that state. But there might be a global optimum to this solution, but it doesn't really have a way of getting there, right? And it turns out that if you look at it as a classical computational problem, what this is actually the same thing as having just variables as zeros and one, and it's a quadratic unconstrained optimization problem. And you know very well that this is an NP-hard problem in general. So there's a one-to-one correspondence between these two problems, and so it happens that whatever is physically difficult to do is also computationally hard. It's a very natural correspondence. And this is where quantum physics offers something interesting. So this is what quantum annealing is about. So what you do now is you create an equal superposition of all of your magnets. So in a quantum system, you would create a magnet plus sub and minus one in a superposition with equal probabilities for every single site. Okay? And starting from that configuration, you slowly change your system into the system whose energy you are interested in, which is that thing over there. So this configuration of different things. And if you follow something called the adiabatic pathway, then you end up with the global optimum of that problem. And this sounds like that, hey, with quantum annealing, I can just have my NP-hard problem and just solve it fast. But the critical thing is that that's one thing that you're following the adiabatic pathway, but there's a speed limit. If you are going too fast, if you do this quantum annealing too fast, then you jump out from the global optimum and you end up in some other local optimum. And to calculate this speed limit is actually harder than solving your original problem, which is a major theoretical obstacle to quantum annealing. So what you actually do is that you anneal 1,000 times, and then you pick the configuration with the lowest energy as your global optimum. But you don't really know whether it's the global optimum. So that's when you do it, for instance, in D-Wave. That's what the 2048 qubits do. So these 2048 qubits, you can think of them as some kind of an equivalent of a magnet. And then you create this superposition of the magnets, and then you finally read out some solution. And the second way of doing it is by something called quantum approximate optimization algorithm, which achieves something very similar using a gate model quantum computer. So it was inspired by quantum annealing. And if you look at the history of quantum algorithms, between 1995, the early days of quantum computing, until, say, 2013, every single quantum algorithm that was developed was targeting this remote future, massively scalable quantum computer that we are never going to have. And that's the kind of a mentality that gives you the exponential advantage. People were chasing that. And what changed in 2013, that's when the first algorithm came out that admitted that our quantum computers are imperfect, We only have a handful of qubits, and the circuits are short. So the question is, like, can we get any advantage with these quantum computers? And so one of the first algorithms that did this was exactly this quantum approximate optimization algorithm. So it was inspired by annealing, and what it does, it tries to find or tries to approximate this adiabatic pathway, but with a gate model quantum computer. So what it does, it discretizes these steps. So every single one of these steps is just a short burst of calculation on the actual quantum device. So you extract classical information, and based on that, you do a completely ordinary gradient descent, and you try to get closer and closer to the optimal solution, and eventually converge to this point where your optimal solution is. And it has pretty reasonable theoretical guarantees of what's the overlap between your solution and the optimal solution. So it was a major advance and a major shift in how we think about quantum algorithms. And now this algorithm is one of the first candidates to show quantum supremacy, to show that you can do something actually faster on a quantum computer.
So how do you get this gradient for the optimization?
So what you're optimizing over is the duration of these things, right? So you get out some value here. So you end up, for instance, here, which is some value of the energy, and based on that, you define a gradient on the parameters, and hopefully that gradient will pull you here to the optimal solution.
But is it really the calculation of the gradient, or like is it some black box optimization?
It's some black box optimization just to tune your parameters. So there are first order methods, second order methods. People try different things. People try various machine learning algorithms to fine tune this. There are tons of things that you can do here, but you can also change like what are the kind of bursts you do here. So not just the duration, but also like the kind of Hamiltonian that you use. So yep.
So is my understanding correct that, okay, so this gate model quantum computer with this algorithm can emulate the quantum annealing, right?
It's very strange, but yes. So because
I don't know quantum annealing itself is like better than classical algorithms.
So for instance, the actual quantum annealer that we have built, for instance, what D-Wave has, it's likes certain parameter settings. So for instance, if you are close to the hardware connectivity, and then you have a disordered system, which means that your couplings are roughly in the same range, but they are quite random. So that's a sweet spot. But correct me if I'm wrong.
Yeah, that sounds right.
Yeah, and this is already the kind of problem that's difficult to solve on a classical computer. So that's where you can actually measure some advantage. Like if you really craft your problems very carefully to fit the hardware perfectly, that's what Google did 3 years ago, and that's how they achieved 100 million times speed up. But that's a very dangerous claim, because they worked for a year to actually fit a perfect problem for the hardware. And what we are seeing today is that you are starting to see an advantage. There's some constant time speed up in problems that you are interested in. And that's again a major shift. So you no longer have to handcraft the problem just to see an advantage for the sake of seeing an advantage, but now you start to see advantages in problems that are actually relevant. And it's very strange that inspiration came from quantum annealing for the gate model paradigm, but that's what happened. And now it became like a cookbook, because over this last 19 years, there have been many algorithms to fit the quantum annealing paradigm. Okay? And now the way to come up with a new algorithm in this hybrid classical quantum gate model is to take the annealing algorithm, do some discretization like this, and then you have a paper. Yeah. All right. But the problem with both approaches, whether it's actual annealing or whether this is this approximate optimization, is that you don't know how far you are from the global optimum. So fine, it gives you some solution, but it comes with absolutely no guarantee of how far you are from the actual global optimum. Until 2 months ago, when we published a paper on how to do this. So all of these values that you pull out from quantum chip will be either the global optimum or some low-lying local optimum. So you will be either in the ground state or above it. And every classical algorithm that you can use, whether that's simulated annealing or some genetic algorithm or whatever you throw at it, is also going to be an upper bound on the global minimum or the global minimum. And we use the convex relaxations and a handful of other tricks to get a lower bound. So now if your solution is here and we get a lower bound here with a classical algorithm, then you can tell like roughly what's the difference between the two. So if it's within a certain range, then you can just take that as your solution. And if you're not happy, then you can go back to your quantum algorithm and run it a few more times to get a better value. Yep.
Does this scale well with the size of the system?
It scales very well with the size of the system. It doesn't scale very well with the connectivity. And that's why it's very good for verifying quantum optimizers that we have today, because they are sparse anyway. And okay, but that discrete optimization in machine learning, right? So this is where there is this complete mismatch between, say, deep learning and quantum computing. Because in a deep learning network, you have millions, possibly billions of weights. And every single weight is at least a 32-bit precision number. And you have a maximum 2048 qubits. So you could embed a tiny little neural network on the largest chip that we have that costs $50 million. So just don't try to optimize a deep learning network on these things. That's a meaningless problem. You have to look at problems which are quintessentially discrete. And there you can get an advantage. So one of my favorite is, I just love ensemble methods. And they're still, like when you look at Kaggle competitions, and then you see that even the ones which use deep learning networks usually combine deep learning networks in some ensemble to get to the top place. And this paradigm fits quantum computers very well, because you always have just a finite number or a small number of models that you are combined. 10, 200, and that's it. So it maps very naturally to some kind of optimization that you can do in a quantum computer. And one of the earliest algorithms, one of the earliest quantum machine learning algorithms ever was doing this. It's called QBoost. It originally came out in 2008. It was a demonstration at NIPS. Back then, it was possible to get into NIPS with a reasonable effort. And this algorithm was dusted off a year ago. And it was used to rediscover the Higgs boson. And the Higgs boson was already discovered. That's not the point. The point is that the Higgs boson was discovered by extremely deep neural networks with billions of weights. So this neural network did not give you any physical insight on like what exactly the physical process was and how it deviated from theoretical predictions. And the model that they trained with QBoost is a shallow network. So it gives you a lot more insight on the underlying physics of how the Higgs boson decay mechanism happened. So it's actually very interesting to uncover some new physics. And by last year, this also meant that an actual quantum processor was on the scale that it could discover the Higgs boson, which I find remarkable in its own right. And there's a lot more here. So you guys know a lot more about meta learning. There are also similar ideas floating around. Then another bigger area is unsupervised learning. So as long as you can map your unsupervised learning to some kind of a graph problem, that's a win, because that's something that you can probably map to some optimization and solve it in a quantum computer. Like one idea is a dense subgraph identification, which you can use for some kind of a clustering algorithm. Okay, so that's all about optimization. Then the most natural thing to do on a quantum system is sampling, is measuring it. Because a quantum state is just a probability distribution. And what do you do with a probability distribution? You sample it. So let's see what exactly happens. So this is the energy distribution of your quantum state, say at the end of some annealing process. And what you are hoping to get is the global optimum. So that would be this lowest lying energy state. But that's not what happens, because you interact with the environment. You start to equilibrate with the environment. And this is the same process what that happens to a hot cup of coffee, for instance. If you leave it in a room for long enough time, it will attain the temperature of the room. That's exactly what the quantum processor does with the environment. It equilibrates and it attains the temperature of the environment. So because of that, you very often don't get the lowest lying energy state, but you get some distribution of different energy values. And it turns out that this distribution that you're sampling, so this quantum state that you're sampling, corresponds to a Boltzmann distribution, or you also call it a Gibbs distribution. And when you think about the Boltzmann distribution, it is a global normalization. It has a partition function. And every time you see a partition function, you probably scream because it's just difficult to calculate with classical resources. You have to do some Markov chain Monte Carlo method, and you have to make sure that they burn in, and then you get out samples that you want just to estimate your partition function. Whereas here, you can just pull out samples from a quantum computer and get your samples from a Boltzmann distribution. So this is what you are exploiting in, say, training Boltzmann machines on a quantum computer. So you pull out your samples, and then you have some probabilistic graphical model, a Boltzmann machine, or some Markov random field, but it also works for Bayesian networks. But this is one big application area, because all of these architectures require sampling from a Boltzmann distribution during training or even during inference. And in general, this is a Sharpie problem, so it's definitely something that's meaningful to solve. And like pulling out these samples from a quantum computer is 50 milliseconds. It's a constant time. Just get the samples out. And I really think that there's a lot more to explore here. So this is, again, one of my own works. I was looking at Markov logic networks. And if you're not familiar with them, what you do is you have like this good old-fashioned AI way of thinking, that you have first-order logic formulas, and then you use these formulas to generate Markov networks. And the good thing about it is that it generates a Markov network that has this sparse structure. So there's a limited connectivity in this Markov network. And if you follow along, our quantum devices have a limited connectivity anyway, so it's very important that whatever you train just naturally fits the underlying structure of the quantum chip. But there's even more. So I got very excited about probabilistic programming. So if you have expertise in probabilistic programming, I would love to talk to you, because there are all sorts of interesting crossovers between quantum mechanics and probabilistic programming. So this is our upcoming paper. It's not on arXiv yet, but it should be on arXiv soon enough, where we explore how we can use probabilistic programming for simulating quantum correlations. And this could be a fertile ground for research, which could be beneficial both for the AI community and also for modeling in quantum physics. Okay, so the next big area is evaluating kernel functions. And if you are into deep learning, then you might say, blah, who cares about kernel methods? But what's exciting here is that quantum computers give rise to a variety of very interesting kernel functions. They just naturally implement them. This one is on a photonic circuit. And we can ask the question, okay, so now we have a machine that can just naturally calculate these kernels for free, essentially. Like, what can we use them for? And what you can use them for is that you can construct these hybrid architectures. So you can have some neural network and then calculate some funky kernel in the middle with a quantum device, and then continue with your neural network. So your quantum device just becomes one layer in your neural network. And then, so these are ongoing experiments of what this is actually useful for. But like one conjecture is that by plugging in a quantum device in the middle and calculating these funky kernels, you can become more robust against adversarial attacks. Okay, so it's a bit in the air at the moment. I was not able to prove it yet, but I'm working on it. So this is another fun area to research. Now, these three application areas, optimization, sampling, and evaluating kernels, use the same kind of logic. So you start with classical data, and we finish with classical data, and you do some quantum stuff in the middle. And it doesn't have to be that way. So you can also think about problems where you start with a quantum state and you end with a quantum state, and then you do some learning on this quantum state. Okay?
Sorry, can you give an example? So I've heard this phrase so many times, but I've never understood what an example of this problem looks like. So
yeah, so imagine that you have a quantum RAM.
okay,
Yeah.
that's another.
Yeah, that's a big if. So if you have a quantum RAM, would be just like the RAM in your computer, but it would return quantum states, and it would also be returned to you quantum states in a superposition. Okay, but it's a completely open question whether it can be built at all, and there are various proposals, and some claim it's realistic, some claim it's completely unrealistic, but that could be a source of quantum states. Another source of quantum states could be, for instance, some quantum simulation. So for instance, you have your quantum computer simulating some molecule, and as the solution progresses, once it gets to a shape that you like, then you can do some machine learning on it. That's another example. And what's a terrible idea is to do state preparation and then tomography. So this means that, hey, you have classical data lying around, and then you want to create the corresponding quantum state, and then do your quantum algorithm, and then just go back to and then understand what the quantum state is at the end. The problem with this is that state preparation would also need a circuit, and it could be potentially a very deep circuit, so that's already a big no. And then on the other hand, if to understand what the quantum state is at the end of it, you would have to keep sampling it over and over and over again until you have a complete understanding of what it is. This is called tomography, and it's a horribly expensive operation. So whatever quantum advantage you would get in the middle by the quantum calculation goes away by state preparation and tomography. So these protocols are meaningful only if you have a source of quantum states and you are happy with a quantum state as your end result. But if you can do this and your quantum computer is big enough, then this is where you can get an exponential advantage, because this is where you can use certain linear algebra operations which are a natural fit for quantum computers. Like one example is matrix inversion. So matrix inversion can be done, in theory, exponentially faster on a quantum computer. And this is where things go really, really wrong in quantum machine learning, because if you look at all papers published on quantum machine learning, 50% of them use the same idea. Hey, there is this machine learning algorithm that I don't understand, but I can twist it in a way that there's a matrix inversion in it. Then I can just use this protocol, have an exponentially faster learning algorithm, and I have my papers published. But it's not really a meaningful problem, and I got very upset about people just using the same idea over and over again. And so we did a bit of a tongue-in-cheek paper. It was published, it's on archive since June. It's Bayesian deep learning on a quantum computer. And so we wanted to develop a protocol that does this matrix inversion, and we wanted to show just how bad it is. And okay, so the paper actually has some mathematics, so there is actual meaning to the paper, but the actual punchline of the paper is the experimental section. So we are going to see how bad it is in a moment, but because we ran it on actual quantum computers on IBM and Rigetti, and IBM was so happy with our results that this is my PhD student, one of the authors, that they gave us a best paper award. And then the other quantum computing company, Rigetti, is also so happy with it that we are going to be featured on the blog. And this is how bad it is. So we measure the probability of the success of the algorithm, and we throw various noise models at it, and we see, as you add noise, then your success rate goes down. But this is all simulated. And this is the actual hardware. So with IBM, this is what you achieve, and this is what you achieve with Rigetti. And if you translate this success probability into like how much your actual state at the end is what you want it to be, just called fidelity, then IBM achieves about 76% fidelity. So there is some overlap, but you would want a more accurate calculation, right? And we are talking about a 2x2 matrix, And when you translate the 50% success rate into this fidelity, that means that you had basically zero overlap between the correct calculation and what you get from the quantum processor because of this decoherence, because of the interaction with the environment. So this zero fidelity is your exponential advantage over inverting a 2x2 matrix. So you have to be very, 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 very careful when it comes to these more abstract algorithms. But to be fair to Rigetti, it wasn't entirely their fault that we got this poor success rate, because their 19-qubit chip just failed before we ran these experiments. So they gave us their older chip, which was performing a lot worse than, for instance, IBM. The new chip is giving better results, but still, this algorithm remains unrealistic. Anyway, irrespective of which paradigms you are interested in quantum machine learning, you are at the very heart of it, because there's lots of action happening in quantum machine learning in this city. So first of all, the authors of the only two books on quantum machine learning work here. I happen to be one of them. And the other is Maria Schult, who works for this startup called Xanadu, who are building a photonic quantum computer just down the road. And they are actually coming to Vector next week. They are giving a talk on next Thursday at 4 p.m. About quantum machine learning, I guess.
Yeah.
And then we have an entire program focused on quantum machine learning, where we try to incubate startups using quantum computers for machine learning. We are in the second cohort. In every cohort, we take in 20 companies, and there are some fun success stories so far. So every 2 weeks, we have this seminar series, so it's going to be next Thursday. And we are organizing a QML workshop in Rotman. This is going to be mid-December. If you're interested in it, just drop me an email. And I'm putting together a massively open online course on quantum machine learning, which I plan to launch in February next year. And if you are interested in this, I'm preparing a lot of material for this course, and I need beta testers who would tell me how bad it is. So if you are interested in becoming a beta tester, then please reach out to me. And that's it. So I think machine learning is just a very good first target application area for these imperfect quantum computers that we have today for a number of reasons. And I think they can solve the kind of problems that are just difficult to attack with classical resources. And that's what research should be focusing on. Thank you very much.